Dino Bektesevic, please.
Is that close enough?
Thank you so much for being so considerate. And his presentation on a gateway to astronomical image processing from the Reuben Observatory Science Pipeline with AWS. Take it away.
Hello, everyone. My name is Dino Bektesevic, and I want to tell you a little bit about gateway to astronomical image processing we've been working on for the past year, aka VRC Reuben Observatory, LSST science pipelines on AWS. So what do all these words mean? Reuben Observatory is an 8-meter telescope currently under construction in Chile, on which the legacy survey of space and time, or LSST sky survey, will be conducted on. The picture of the site you see on the left was taken last week on October 8th, and as you can see, the building is nearing its completion, and the project is due to start soon. The goal of the project is to conduct a 10-year survey of the sky every 3 nights for over 10 years, and as already hinted at, this means that the produced data volumes will be very large. For example, previous sky surveys, such as Sloan Digital Sky Survey that ran from 2000 onwards, or Pan-STARRS that ran from 2010 onwards, collected 116 terabytes and 1.6 petabytes of data respectively. And this is still significantly smaller than what Reuben Observatory can do in just a year. The data volume produced by Reuben is kind of a novelty in optical astronomy, and so the question of how to process and share that data with a wider astronomical community received a lot of focus. The project itself will reduce the data using 2 supercomputing facilities, one being NCSA in Illinois, and the other being CCIN2P3 in France. These supercomputing facilities will also be used to give scientists access to the services and data they need, and about 10% of them will be devoted as user-shared compute resources. And while this is not an insignificant amount of compute resources, and while it's true that primary focus for many astronomers will be catalogs, which will be smaller, given the data sizes, the allocated resources are not one-size-fits-all solution. So we started asking ourselves, can we do a bit better? Could we build a system that would allow users to analyze data at the scale of Rubin? Could they use that to speed up their science? Could it be affordable, easy to use, and could it support users that want to do a custom analysis of the data not provided by Rubin? The need for scalability and shareability while maintaining the low cost naturally led us to the cloud compute model. At this point, a shameless plug from my colleague, Steven Stetzler. If you haven't seen his talk earlier today, I definitely recommend you watch it. It discusses many topics related to this talk, specifically on how they give users a Jupyter interface to a platform that is able to process catalogs in the cloud at scale. But while they focus more on the interface and catalog in their talk, in this talk, we'll focus more on the image analytics. We wanted to leverage the existing state-of-the-art functionality in astronomical data reduction that's already part of the Rubin LSST science pipelines. The science pipelines enable processing of astronomical data from a single exposure to joint calibration of multiple exposures, and they also support multiple different instruments, not just Rubin, which is a big plus. Science pipelines are also well suited to lift and shift migration to the cloud, since they abstract all their input-output operations away from the actual algorithm implementations. That I abstraction is called the data butler. The purpose of the butler is to isolate the end users from file organization, file types, related file access mechanisms by exposing data as Python objects. Data sets are referred to by their unique IDs that are resolved through a registry and then retrieved from a data store. So the data store is the actual file storage of the data, like a POSIX file system, for example, and the registry holds all the data relationships and is usually backed by some database management system. So to zoom out a little bit and tell you how the data butler ties into the science pipelines, I'm showing you a schematic representation of Rubin middleware component, which ties the two components together, with the data butler being here on the left and the science pipelines kind of being everything on the right-hand side. Science pipelines consist of tasks that can be chained together into a pipeline, right? And such a pipeline is described by a directed acyclic graph, or a DAG, called a quantum graph. Each quantum, a node in the graph, is a task applied to an individual data set, kind of bundled together. Since the data butler interfaces all of the I/O for every task in science pipelines, it should be obvious that adding appropriate functionality to the registry in the data store effectively enables the science pipelines to run in a cloud environment. We opted to attempt to do this with AWS because they're one of the most mature cloud service providers. And we did it by implementing simple storage service functionality, or SG functionality, as the backbone of the data store, and then PostgreSQL as the backbone of the registry. And then we used AWS Relational Database Service, or RDS, to launch Postgres databases in AWS. To acquire computer resources, we used AWS Elastic Compute Cloud Service, or EC2 service. So how far does this get us? In effect, these changes allowed us to execute a quantum graph from a single EC2 instance with the output persisted into S3 and RDS. That's already pretty cool, since there are already a large collection of most commonly used tasks in astronomy within the science pipelines. Plus, users can write their own tasks that should kind of automatically work for all supported instruments. On top of that, making a quantum graph is also relatively easy and effectively boils down to writing a YAML config file that lists all the tasks you want and their configuration. What we are missing to scale out here, however, is a way to procure and manage the compute instances involved, some way of converting the quantum graph into a series of self-contained executable scripts that can be scheduled in the correct sequence on appropriately matched resources. And these roles are fulfilled in tandem by Pegasus Workflow Management System, version 5.0, which also has a poster in this conference, you should definitely check out, and HD Condor. So we convert the quantum graph into an abstract workflow using the Pegasus API. The abstract workflow is then in the planning stage, converted into a set of stage-in, executable, stage-in and stage-out scripts, and an executable DAG that can be executed by HD Condor. HD Condor executes the executable workflow by effectively matching the jobs and their requirements to appropriate compute slots located in the HD Condor compute pool. The pool can be dynamically resized by adding and removing instances from it, including EC2 instances. HD Condor Annex is the module that provides that functionality. Annex can dynamically add instances to the pool and then dynamically deallocate them after an absolute set time has elapsed, or the instances are recording as idling for longer than some set time. Zooming back out again to show you what the build system looks like, you can see that the user acquires a head node into which they log in. They create a quantum graph, convert it to an abstract workflow and submit it to Pegasus, and then they procure compute resources using HD Condor Annex. And the rest is automatic. After the workflow is completed, the instances are automatically deallocated, and this greatly reduces cost. If the user can still access data from the head node if they want to perform further analysis. We tested the performance and the cost of this system by executing workflows of different complexity and size and different types and sizes of the EC2 instances. The goal of the testing was to establish rough estimates of the stability performance and the cost of running. We found, though, that without further configuration of the RDS service and the workflow execution, the performance is quite poor. For example, allocating more cache per connection, increasing maximum number of connections, job clustering, staging in of the raw data, staging out of the execution logs, etc., all had a big impact on the performance. Preliminary results showed us that resolving these bottlenecks, many always related to I/O on the compute nodes themselves, can relate up to 50% decrease in time it takes to execute the workflow, and consequently a similar decrease in total cost per execution. An important note about the shown graph is that testing without optimization results in large variance in measured wall times of workflows, especially if the workflows are executed consecutively due to the nature of these bottlenecks. And I mentioned this because the figure in the slide does not convey this fact as obvious as one would want. We are working on getting a more representative set of timings that have error bars and etc. that will show this. The data set we used in this analysis represents about 11% of the number of nightly observations of Rubin. In absolute terms, it's about 0.2 terabytes of input data and 2.7 terabytes in terms of output size. The workflow we made for this analysis consists of 4 tasks only, of which the first one is the initialization task that takes like 25 minutes. In principle, this task would only be run would only have to be run once for the lifetime of a collection in the data repository, but for technical reasons had to be run for every test we perform. And finally, the slide everybody's probably going to be looking for. These are our preliminary cost estimate for example workflow. We find that the cost is approximately constant for tests using 25 and 50 workers, and this is to be expected as the cost of more powerful instances and more instances in general is offset by reduction in total wall time required to finish a workflow. But this also means that if the cluster is oversubscribed, adding more instances or using more powerful EC2 instances decreases the wall time, but keeps the cost constant. And that's a very exciting prospect to think about. Another cool data point to consider is this singular spot instance test. Spot instances are rented by AWS to users that require them, but can be deallocated at any time with a 2-minute notice. This requires a fault-tolerant software, but at the time of development of this project, Science Pipelines didn't quite yet handle failing and restarting jobs very well, so it didn't perform many tests using spot instances. But in this case, it's also obvious that cost could be another factor of 4 smaller compared to on-demand instances. For 100 sized instance clusters, the data is a bit all over the place because the data set we used wasn't really big enough to saturate the cluster, and whether the instance would idle and get deallocated or not was a bit of a gamble with the scheduler, so the data is not overall very reliable. We also attempted to construct a comparison of compute resources, cost of compute resources only for an in-cloud versus on-premise deployment. And we find that if these optimizations apply or can be extended across the entire planned data release production workload, the workload LSSD will be running in production, that Rubin yearly DRP processing cost in the cloud would be between 600,000 and 900,000 United States dollars. And note that this does not include long-term archival storage, but does include the storage required to store the test data and execute the workflow. And this estimate is comparable to the first-year cost estimate of Rubin on-premise compute resource deployment, which is estimated to be around 700,000 United States dollars. Word to the wise, however, the Science Pipelines, Data Butler, middleware, all these components are active development and their performance varies between releases. And since we're extrapolating absolute costs from small data sets like these, given these facts, conclusions about total cost require really careful consideration. So in conclusion, the design of Rubin Science Pipelines makes them well fit for a lift and shift migration to cloud. By optimizing the system, we could make the compute resources cost comparable to on-premise. And even if they weren't in total grand scheme of things, due to the cost, cloud to cost scaling, it's possible that supplementing on-premise resources with spot or instances would yield net savings in the long run because the science would be delivered more quicker. Of course, more work is required, like these optimizations need to be delivered to a full DRP workflow. Better interface would be very much desired, like integrating Jupyter Notebook, but that requires better integration with Pegasus and HD Condom. And that's about it. Thank you very much for your attention. We'll take any questions now if you have.